So for 2.4, we're going to take a look at some of those properties of exponents that you took a look at on Friday. So if you remember the negative exponent property from Friday, so that is 1 over b to the n to make it possible. And the product property, for example, 2 to the second plus 2 to the third is 2 to the fifth. So we add those exponents. Now, so what we're going to take a look at is a horizontal translation and different ways that you can look at it. So for example, if you guys remember, if I had x minus 2 squared, you guys said that moved to the right 2. And if it was outside x squared plus 2, that would be up 2. So if you looked at this translation when it was plus k, what would you say that moved? You'd probably say it moved to the left k. But if you guys remember, our rule of exponents, right, is we add those. So this can really be written as b to the x times b to the k. Right? Because rules of exponents, we add x plus k. Now, this is just really a number. So this is just some random number, a constant there. So we could rewrite that. If we put that out in front, b to the k times b to the x, that's really just some constant value from b to the x. And remember, if it's outside, that is really a vertical dilation. Because, right, it's multiplying on the outside. So every horizontal is equivalent to a vertical dilation. And it's pretty cool how this works here. And again, here's what we've talked about. B to the x plus k, right? B to the x times b to the k, which is really just that constant right there. So let's take a look at it. This is 2 to the x, right? And we have that point 0, 1. And what does this do? This moves it to the left 3. So 1, 2, 3. Here's now the point negative 3, 1. Well, what really happens, right? Because if we were to do this, our rule of exponents, 2 to the x times 2 to the third, so that's really 8 times 2 to the x. So our starting value is now up here at 8. So you can see our original down here, 0, 1, it is that vertical dilation. So let f of x equals 3 of x. Let g of x be the transformation of f. For each problem, name the transformations. And I want us to think of our transformations as what is like we're going to think of it in terms of right, left. Because we could say this is a vertical dilation of 9, right? So we could say vertical dilation of 9. Or how could we rewrite this? This is really 3 squared times 3 to the x. So that's really 3 to the 2 plus x, and I'm just going to write it as x plus 2. So what way does this also move it? Another way would be saying to the left 2. Now what about this next one? So this is really 1 over 27 times 3 to the x. So again, we could say it's a vertical dilation of 1 over 27. Or how can we rewrite that? Well, 27 is 3 cubed. Well, that's in the denominator, so we have to flip it, negative 3, running out of space. So this is really 3 to the x minus 3, so it moved to the right 3. And this last one, so this is 3 to the x over 9. So again, we could pull that out and say this is 1/9 times 3 to the x. So a vertical dilation, I'm just going to put that, of 1/9 of VD. Or what would this be? Well, 1 over 3 squared times 3 to the x. Sorry, that should be a times. Well, let's flip it up. So 3 to the negative 2 times 3 to the x. So that's 3 to the x minus 2, so it's to the right 2. Now we're going to take a look at power properties. So if you remember from Friday, our power property is that we multiply those. So 2 times 3 is 6. So what does this mean? If we have something multiplied together here, again, if it's inside, so that's a horizontal dilation. And if you remember, horizontal is 1 over c. Or again, we could separate this out, right? Because this could be b to the c. So it's going to change our base here. So if I had b to the c to the x, that's a change in the base. So another way of looking at that. So horizontal dilations. B to the cx is equivalent to a change of base of an exponential function. So b to the c, where b to the c is a constant, it's not equal to 0. So if we take a look at this again, we'll start with 2 to the x. So 2 to the 3x, again, this is 1/3 times our x value. So for example, this was at 1, 1, or x, let's see, that'd be, it's not 1, 1. Our original one here is, let's see, 2 to the 0 is 1, 2 to the first is 2. I think our scale might be a little off on that, but we'll still be able to understand this. Okay, so our original is here, and it was a vertical horizontal dilation of 1/3. So it's taking all our exponents. For example, this was 3 and bumping it back to 1. Our scale must be off on that one. But really, this can be 2 to the 3rd to the x, which is really 8 to the x. But we can see that's the same thing because it's going to bump that up higher. So our change of base makes it a bit steeper. So let's take a look. What is the transformation? So of 3 to the x. So what is this really? This is really 3 squared to the x power. So that's really 3 to the 2x. So it's a horizontal dilation of 1/2. So this one, so we have 3 to the x to the -3. So that's 3 to the -3x. So what is that? So that's a horizontal dilation of 1/3. But then what does that negative do? So it's inside, so it's the opposite x value. Which, what does the opposite x value do? Well, if it is here, it would go over to the left. So that reflects over the y-axis. Now the last thing we're going to talk about is the root. So for example, another way of writing b to the 1/2 is the kth root of b. That sounds really weird. So like for example, the square root of 9 is equivalent to 9 to the 1/2. If I have the 3rd root of x, that's equivalent to x to the 1/3. The 5th root of 8, that's equivalent to x to the 1/5. So that root goes on your denominator. So if you needed to find h of 1, 2 times 5 to the 1/2, and now the half becomes a square root. So 2 times the square root of 5 is the more common way you'd see it. So what about this one? Evaluate when it's -2. So times 2 to the -2/3. Well, what do we know a negative does? We flip it. So 6 over 2 to the 2/3. And then again, the bottom one is our root. So 6 over the cubed root of 2 squared. And we could say 2 squared is 4. So the cubed root of 4. So there's all those different ways that you might see this.